our B.1 introduction to quicksort. All right. So the quicksort. So here, let me use a few minutes to explain the name quicksort, why we call it quicksort, why no other sorting algorithm use the quick in its name, why we only call this algorithm quicksort. There is some reason. Okay? The most important reason is it has really good overall performance. So in its title, it emphasizes overall performance. Can we say this is the quickest sorting algorithms in the world? Nobody can claim that. Actually, we can say that there is no known quickest sorting algorithm in the world. Nobody knows that. Okay? But this one, why nobody wants to argue about the name of this one? Because this one has near quickest. You cannot say absolute quickest, but we have no problem to say nearly quickest. Near quickest. Very close to the quickest. Yeah. So really good one. Yeah. So let's learn this interesting algorithm. The same problem again, but why we consider a new sorting algorithm? So the reason is very simple, because our emphasis will be different. All right, so look at the idea first. We still use the divide and conquer, but we use it in a different way. So we put our focus in different aspect. Yeah. Especially when we compare with the merge sort, you will see the place we put our effort will be completely different. So we will compare later. Yeah. The goal, make the overall performance as fast as possible. That's the goal. Yeah. All right. In order to get that overall fast performance, we have to sacrifice a little bit. Yeah. So where do we sacrifice? Here, worst case. In this case, we have very poor worst case performance. All right. But the probability for the worst case is very slow. Yeah. When we run this quicksort many times, so in a very small probability, the worst case is very poor. So if we take the average, we look at the overall, average case performance, we get extremely fast overall, sorting algorithm. Okay? All right. Now let's look at the idea. So we want to look from divide and conquer. The view we use it is different. Yeah. So here I want to do some comparison with the merge sort. So for the merge sort we just learned, let's look at the 3 steps: divide, conquer, combine. These 3 steps. Okay. For the merge sort divide step, very easy. We cut an array in the middle. That's our divide step. Big theta of 1. Now, we need to do some work, calculate the median, right? So separate, small work. Yeah, so that's big theta of 1. Then conquer recursion. Yeah. We call recursive function, so recursion. So combine, we need to spend a lot of time. That's our main step, the merge step. So that is the combine step. And here, you can see I do not use n, I use k here, not the original data size n, because n referred to the original data size. Okay? So this k, think about when we do recursion, so the data size could be quite different. So here it refers to the current data size. Because when you do recursion, that's the data size is your current subarray. Data size of your current subarray. Yeah, so that's the K. All right. Now, the new idea. We want to still use the divide and conquer, but in a completely different view. Yeah. Conquer step still recursion, so we do not want to change at this step. Okay? Still recursion. Then, for the divide and the combine, we want to take the opposite way, opposite to our merge sort. So what's that opposite? So because these two steps, actually, when you work on it, you have to something like trade-off you need to do. If you make the divide step easier, you have to pay high cost in combine step. If you want to make the combine step easier, you have to pay high cost at the divide step. Yeah, so that's the meaning of the trade-off here. But here, let's try an opposite way. So we try to pay the minimum at the combine step. In that situation, we have to pay relatively high cost at the divide step. So that's the way we change the view. Okay. So this new idea, if we try to implement this new idea, that's the quicksort. So that's the one we will learn for the quicksort. All right. Now the question, how to make the combine step easy? Yeah. All right. How much we need to do? Almost do nothing in the combine step. So how can we, so what's the meaning almost do nothing here? Yeah. So let's see. The combine step, big theta of 1, almost do nothing, right? So you need to do a little bit, the minimum. You need to do something, but that's the minimum you can do, right? Yeah. Then the divide step, relatively high cost. So we, yeah. So let's do the easy step first. Yeah. And the harder step, let's delay. Okay, we will spend a lot of time for this key step. Okay, all right. What do you mean you can combine two subarrays in this cost? So let's try to look at the meaning. Yeah. All right. So let's look at these two subarrays. Okay. Before conquer. So here, yeah, we separate somewhere in the middle, somewhere, not necessarily right in the middle, right? Yeah. Before conquer, so each one is not sorted. Okay. All right. Then after conquer, yeah. So eventually we need to conquer each one after another. Yeah. So after conquer, A array is sorted, B array also sorted. Okay. All right. Now we combine them. So, but when we combine them, think about how much we need to do. Our goal, so that's our wish list. We wish to do things like this, our wish list. When combined, do nothing. You just put them together, the whole array is sorted. That's our goal. Okay? We want this happen. Yeah. So the whole array is automatically sorted. If you just put them together, we get the whole array sorted. Okay. Is that possible? Yeah. Yeah. If we can make it possible, make it happen, then the merge step very cheap. So cheap. The cheapest as we can do, right? But there must be some condition here, right? So you have to have some condition. Okay? So we need to know that condition. Under what condition? When we put them together, the whole array sorted. We want to know that condition. Okay? So that's the important thing. So you think about under what conditions, if we put them together, the whole array automatically sorted. It's possible. Yeah. So the condition also actually very simple. Yeah. This is the condition. The value of any element in the A array is less than or equal to the value of any element in the B array. Yeah? If this condition is satisfied after A array is sorted and the B array is sorted, and the maximum element in the A array, okay? So A max, the maximum element in the A array, is still less than or equal to the minimum element in the B array, right? So now you put them together, you get the whole array sorted. Yeah, so that's the condition we want to have. Yeah, all right. But okay, so now we understand this condition. The question is, how can you make that divide step happen? How do you divide two arrays that satisfy this condition? That's not easy. Yeah. So that's why this divide step is very hard. Okay? Yeah. So that's why we need to spend a lot of time on this divide step. Okay. All right. The most important step, this divide step. Yeah. So what's that? We know the requirement. So when we do the divide step, so when we do the division or do the partition, yeah, so later we call it partition, we want to split the original array into two subarrays, A array and a B array, such that any value of an A element is less than or equal to any value of B element. Okay? Yeah. That's the condition. Yeah. But definitely we do not require A array sorted, B array sorted. Not necessary, because that's the recursion. We will use recursion to conquer that, to make both subarrays sorted. Yeah. Yeah. All right. And so we don't worry about that recursion, the conquer step, yeah, because we can assume by recursion call, we can make that happen. Okay? So here you can see the recursion is very powerful. Some very complicated things we can assume by recursion. Yeah, excuse me. All right. Okay. All right. So that's what we need to do in the divide step. We cannot do here, so this is just introduction part. Yeah. So we know what we are going to do in the next part. All right, so that's the B.1.